Hi, we're team number 11 and this is activity 4, a simulation of atherosclerotic plaques to see flow effects in an artery. Here is a table of content where we're going to cover the objectives, the theoretical framework, the main pipeline for CFD analysis, results, and discussion and references. Cardiovascular diseases, CVDs, represent the leading cause of morbidity and mortality worldwide. Atherosclerosis specifically constitutes the cause of about 50% of all deaths in Western society. Development of computational fluid dynamics (CFD) has led to the investigation of specific hemodynamics present in diverse CVDs, such as atherosclerosis. Within these simulations, different parameters are taken into account, relying on the mechanical properties of the vessel, wall, and blood flow.
The aim of this activity is to analyze the hemodynamics in pathological and healthy vessels, and as well to evaluate the vessels under ideal conditions and obtain results such as pressure, velocity, and shear stress plots. Regarding the mechanical properties, our research shows that a healthy artery have a Young modulus of elasticity of 1.47 megapascals to 1.55 megapascals. Meanwhile, a pathological one is reported as 3.77 megapascals to 4.43 megapascals. The density of soft tissue, according to NEST, is reported as almost 1 gram over square centimeter. For the Poisson ratio, both types is reported as approximately 0.49 being the pathological one, a little bit higher as shown. Ultimate tensile stress was reported for both circumferential and longitudinal forces, and for the three layers that made up the arterial wall, being this the intima, the media, and the adventia. And the results are appreciated in the table on the screen. For the properties of blood density, is reported in different values, but most common range near 0.994 grams over milliliter. As well, dynamic viscosity was reported in 3.5 to 5.5 centipoise, is characterized as a non-Newtonian shear thinning fluid.
According to several sources, such as NASA, the first thing to do to understand the problem you have to analyze. Once delimited, you have to import the geometry and make your model watertight to create the mesh. Once finished this process, boundary condition in this case static pressure and inlet velocity will be inserted. If needed goals could be made, subsequently the simulation could be run and obtain the results. Then the post-processing of the result could be done and plots could be created. The pipeline was followed to our activity as shown in this and the next following slides. We have the type internal analysis, fluid blood, ideal condition, and internal measurement system. Next, we have the create leads. Leads are created to make the model watertight. In the boundary condition, we have a static pressure of 120 millimeters of mercury, and inlet velocity of 0.2 meters per second, and next we then run the analysis.
One of the results was that the wall shear stress was higher for the pathological region, approximately 30 pascals, where we observe an increase in respect to the healthy vessel. The shear stress is one of the most important physical forces acting on endothelial cells, where blood flow has a uniform and laminar behavior. The cells are aligned in the direction of flow. However, where the flow is disturbed in the affected area, the cells do not have that orientation and increases permeability to macromolecules such as LDL, that raises the atherosclerosis lesion.
As we can observe in the screen, the velocity in the pathological vessel obstruction is greater than in the healthy vessel in the same area. Also, a decrease in velocity is observed in one of the branches, which we can attribute to the creation of a vortex.
Translating a simulation into visual data, we can clearly see a difference in velocities. Using the continuity equation, we know that the transversal area and velocity in a certain section should maintain a balance across the whole vessel to be analyzed. Given this, we can see in the graph that the velocity in the atherosclerosis cut increased in order to sustain area reduction. To make the graph, firstly, we made two cuts in both vessels, C1 and C2. For the pathological vessel, C2 is a cut at the atherosclerotic area and C1 is at a certain distance before C2. In a healthy vessel, both cuts are intended to be at the same section of the pathological one. However, this was done with approximates. Cut 1 and 2 represent the mean velocity calculated at the respective cut. Therefore, we can see that the velocities in a healthy vessel remain the same, whereas in the pathological one, this velocity had to increase in the cut too, proving this the validation of the continuity equation.
Here we observe that the point with greater pressure is the bifurcation, where the fluid travels to both branches.
Translating the simulation into visual data, we can easily see a difference in pressures. Using the Hagen-Poiseuille equation as a reference, we can understand that a reduction in radius within a lumen, as it happens in atherosclerosis, causes an increase in a delta pressure. Complementing this information as a visual data representation, we use the same cuts as seen in the cut flow velocity. Cut 1 and 2 represent the mean pressure calculated at their respective cut. Given this, in the graph we can see that in a healthy vessel, both cuts don't seem to have a significant delta pressure. However, in the pathological one, we do see a significant difference in pressure. This data, represented as a graph, gives us a better understanding of how the atherosclerotic plaque impacts pressure gradient.
Lastly, we get the flow trajectories of the simulation with the healthy vessels and the pathological vessels.
After all the analysis we have conducted, we proved that the existence of a pathology in a blood vessel, like a reduction of lumen in an atherosclerotic vessel, could affect the hemodynamics in the blood circuit. Thus, the usage of CFD analysis to understand quantitatively the behavior of fluid and the repercussion on the integrity of the arterial wall could be assessed. In the next slide, we have the reference of this work.